In real-world applications, authorization is one of the most critical parts of backend security, but it also one of the most commonly broken. In previous videos, we look at the issues like horizontal and vertical access control, IDOR, and mass assignment. We also have created a permission-based rebate system for scalable system, all demonstrated with a vulnerable demo application and see how to fix these problems. In this video, you will learn how secure authorization is designed from a system perspective and how to secure your application so authorization is centralized, consistent, and hard to bypass. By the end of this video, you will not just understand what authorization is, you will also understand how to design it properly so it stays secure even as your system scales. So let's get started. Our first method is the principle of least privileges. This means every user, service, or a system should have only the minimum permissions required to perform its job and nothing more. It sounds simple, but in real-world authorization systems, this is one of the strongest defenses against data leaks, privilege abuse, and system-wide breaches. Let's understand why it's so important. It minimizes the blast radius of a breach. This means any access you grant is something an attacker can potentially abuse if that identity gets compromised. With principle of least privileges, this damage stays contained. A narrow privilege scope means a breach affects only a small part of the system, and our privilege count turns a small compromise into a total system access. In other words, without principle of least privileges, one leaked credential can become a full system takeover. Insider threat mitigation. Not all attacks are external. A employee, a contractor, or a compromised internal account can cause serious damage. Principle of least privileges ensures that even trusted insiders can only access what their role strictly requires. A junior developer should not be able to query the production payment table just because they have a database account. Accidental damage prevention. Humans make mistakes. A developer running a script against the wrong environment, a misconfigured automation job, a fat-fingered CLI command, these cause real incidents. If the account running that script only has read access, a mistake is embarrassing. If it has right to delete access everywhere, it's a disaster. Principle of least privileges protects you from yourself. At its core, principle of least privileges is not about restricting productivity, it's about containing failure. Because in real systems, the question is never, will something go wrong? It's about how far will it separate when it does. One of the most important principles in authorization design is deny by default. The idea is very simple. If a user is not specifically allowed to perform an action, the system should automatically deny access. Instead of asking, should we block this request, we should ask, do we have a rule that allows this request? This approach significantly reduces the chance of authorization mistakes and accidental exposure of sensitive functionality. A common mistake is building systems where access is allowed unless a specific restriction exists. Developers might add authorization checks for few sensitive endpoints and assume everything else is safe. However, as the application grows, new routes, new features, and new roles are introduced. If authorization checks are forgotten on just one endpoint, users may gain access to resources or functionalities they should never use. This often leads to serious vulnerabilities. In this series, we have built a permission-based rebate system that follows the deny by default principle. As you can see in this endpoint, we must specifically define a permission before anyone can access it. We then manually assign that permission to appropriate roles of users we want to allow access. Access is only granted when the authorization system finds a matching permission. If no permission is defined or assigned for a particular endpoint, that API will not be accessible by anyone by default. This ensures that access is only granted intentionally and helps prevent authorization mistakes that could expose sensitive functionalities. And forgotten authorization checks become much less dangerous because the default behavior is to block access. Deny by default follow a simple security mindset. If access is not specifically allowed, it must be denied. These principles help prevent authorization vulnerabilities, reduce the impact of configuration mistakes, and create a much safer foundation for building more secure applications. Our next secure authorization technique is backend enforcement. This means authorization decisions must always be enforced on the server side, not just in the front-end applications. A common mistake developers make is relying on the user interface for security. For example, suppose only administrators should be able to delete courses. The front end hides the delete course button from regular users, so everything appears secure. But there is a problem. Attackers do not need your front end. They can use tools like Postman, curl, or Burp Suite to send requests directly to your API. If the backend does not verify permissions, the attacker can simply call the delete endpoint and perform actions they should never be allowed to perform. This leads to vulnerabilities such as broken functional level authorization, where user can access functionality beyond their intended privileges. To prevent this, every sensitive endpoint must perform authorization checks before executing any action. The key principle is simple. The front end can improve the user experience, but the backend must provide the security. Never trust the client, always verify the permission on the server before processing a request. Now let's talk about another important authorization design principle, centralized authorization. Centralized authorization means that access control decisions are enforced from a single consistent location rather than being scattered throughout the application. Instead of every developer writing their own authorization check inside controllers, services, or routes, the application uses a common authorization mechanism such as middleware policies or permission services. In the previous video, we designed a permission-based RABEX system where all roles and permissions were managed in a centralized manner. If you have not watched that video yet, I recommend checking it out first as it provides the foundation for what we will discuss in this video. Centralized authorization provides several important security and maintenance benefits. It makes authorization logic easier to understand because access control decisions are managed from a single location instead of being scattered throughout the application. This helps reduce implementation mistakes and security vulnerabilities caused by inconsistent checks. Finally, when new roles, permissions, or access policies need to be added, changes can be made in one place, making the system easier to maintain and scale over time. The next secure authorization technique is resource ownership check. A permission-based ownership check alone is often not enough to secure an application. Resource ownership checks ensure that a user can only access or modify resources they actually own, unless they have a special permission such as an admin privileges. For example, a user may have a permission to access the profile update route. The permission check confirms that the user can perform the update profile action, but it does not verify which profile is being updated. Without a resource ownership check, the user could potentially update another user profile record instead of their own. This is where resource ownership checks become important. The idea is simple. Before granting access, the application verifies whether the requested resource actually belongs to the current user. Think of authorization as answering two separate questions. First, does the user have permission to perform this action? And second, does the user have permission to perform this action on this specific resource? Many authorization vulnerabilities happen because developers only answer the first question and forget the second. Resource ownership checks are one of the most effective defenses against broken object level authorization. BOLA. BOLA is very common authorization vulnerability and is ranked as the number one risk in the OWASP API Security Top 10 because it allows attackers to access or modify resources belonging to other users. We have already covered how to implement resource ownership check and prevent BOLA vulnerabilities in previous videos. If you like to see the practical implementation, be sure to check them out. In the previous method, we focus on questions like can a user can access this endpoint and can a user can access this resource. But the authorization does not stop there. Even when a user is allowed to access a resource, they should not necessarily be allowed to view or modify every field within that resource. For example, a user may be allowed to update their profile, but should they be able to update their role, account status, or verification flags? Imagine if the application mistakenly allowed the role field to be modified, a normal student could simply change their role from student to admin. As a result, the user would instantly gain access to administrator-only functionality throughout the system. This is a classic example of mass assignment vulnerability, where the application accepts and updates sensitive fields that should never be controlled by the user. Similarly, when returning data to users, we should never expose sensitive fields in API responses. For example, password hashes, reset tokens, internal nodes, or security-related fields should not be sent to client-side. Just because a user is allowed to access a resource doesn't mean they should be able to view every field within that resource. Field level authorization helps ensure users only receive the data they are authorized to view. We have already covered mass assignment and vertical access control vulnerabilities in a dedicated video with a practical demonstration, so feel free to check that out if you like to learn more. To solve this problem, we need to define which fields users are allowed to read, update, or access for a particular endpoint or operation. Instead of blindly trusting the incoming request or returning entire database objects, the application should validate and filter data before it reaches the business logic and before it is sent back to the client side. A common approach is to create a request DTOs and response DTOs. DTOs means data transfer objects. These DTOs define exactly which fields are allowed. Any field that is not defined should be rejected or filtered out. For example, if a user is updating their profile, the DTO might only allow fields such as name and email. If a attacker sends additional field like role, that will never reach the update profile function logic because they are not part of the allowed schema. The same concepts apply to responses. Rather than returning an entire database record, a response DTO can define exactly which field should be sent to the client. Sensitive fields such as password hashes, reset tokens, internal nodes, or security-related attributes can be automatically excluded. To make this easier to maintain, it is recommended to use a centralized DTO approach, where all the request and response schemas are defined in one place. This creates a single resource of truth for data validation and filtering across the application. It also makes security reviews easier because developers can quickly see what data each endpoint accepts and returns. Fortunately, there are several popular libraries in JavaScript ecosystem designed specially for this purpose. Libraries such as Zord, Joy, and Class Validator allow developers to define schemas, validate incoming data, enforce data types, and filter unauthorized fields in a consistent and centralized manner. By combining centralized DTOs with proper authorization checks, we can effectively implement field-level authorization, prevent mass assignment vulnerabilities, reduce accidental data exposure, and ensures users can only read and modify the data they are authorized to access. In a secure application design, adding authorization once is not enough. Even if your ABAC system, permission checks, and ownership rules are correctly implemented, security can still break over time. That's where regular authorization testing becomes critical. Regular authorization testing means continuously verifying that access control rules still work correctly after every change in the system. Because in real-world applications, most authorization bugs do not happen during initial development. They happen later when a new feature are added, endpoints are modified, or middleware is accidentally skipped. Regular testing helps prevent this kind of security regression. It includes manual testing during development, where you try accessing endpoints using different user roles and attempt unauthorized actions. It also includes automated testing, where user defines security test cases like a normal user should not access admin routes, a user should only access their own resources, and most importantly, it includes negative testing, checking what should not be allowed, such as modifying IDs, changing roles in the request, or accessing endpoints without authentication. In short, regular authorization testing ensures your security does not degrade over time, because authorization is not a one-time setup, it is a continuous validating process. So throughout this video, we have covered some of the most important methods for designing secure authorization systems. We have discussed the principle of least privileges, ensuring users receive only the permissions they truly needed. We looked at centralized authorization, which helps keep access control logic consistent, maintainable, and easier to review. We covered deny by default, where access is blocked unless it is explicitly granted. We explored backend enforcement, ensuring authorization checks happen on the server and cannot be bypassed from the client side. We discussed resource ownership checks, which helps prevent users from accessing resources that belong to someone else and help protect against vulnerabilities. We looked at field level authorization, controlling not only which resources user can access, but also which specific fields they can view or modify. And finally, we covered regular authorization testing, which helps ensure security rules continue to work correctly as the application evolves. No single technique is enough on its own. Secure authorization comes from combining these methods into a layered defense strategy. If you are building APIs, web applications, or microservices, implementing these practices will significantly reduce the risk of broken access control vulnerabilities and make your system much more resilient against attacks. I hope this video helps you better understand how secure authorization system should be designed in a real world applications. If you found it useful, consider liking the video and subscribing to the channel for more content on the application security, API security, authentication, authorization, and secure software design.